Okay, so let's continue our lecture. Well, I will explain this part again in detail. Yeah, I will explain each block of this architecture. Okay, first, what you have from modeling is this equation that tells you if you supply a certain voltage, then you can have the angular velocity of the motor that can be computed via this differential equation. And we can rewrite this by omega substituting omega by theta dot. So here you got theta double dot and omega here is theta dot. Then uh, we build a block diagram that make you convenient to have analysis as well as building simulating model to make simulation. So first the systems. So this part is system, or you can say plant. Okay. Eh, Again, here you have the input as a voltage. Is you supplied voltage, certain voltage VA, then you can compute uh, the right hand side of the differential equation, which is theta double dot. Okay, and then you put the numerical integrator here, then you have theta dot. And because in this system model you need to compute the right hand side from theta dot, that's why you need to give feedback here theta dot to here. Okay, and here in numerical integrator to integrate theta dot to get theta. This is what it means. So um, in summary, for the plant, oh, sorry, I made a mistake. The plant itself, from the input as voltage and output as theta, the plant itself cover this part. Yeah, actually this part, this plant, or you can say system. Okay, but the way I build architecture here is to give you detail how you can make a simulating model. Okay, then you want to design a controller to control angle of the motor. So you need to measure the angle of the rotor. Okay, so here suppose you can measure, then you can have the value of the measure theta, and then you can easily compute the error between the desired and the actual. From this, you design a controller which is called proportional controller, computed by the multiplication between the error and a constant Kp. Okay, so voltage, the supply voltage is calculated from the multiplication of these two terms, right? Then you can write the differential equation with the input as theta d, your desired. You said you desire this, and what happened with the actual. Okay, so here is the derivation of the model of the feedback control. Um, you start from this equation and then substitute supply voltage VA by theta E error theta times Kp. Um, so the error theta times Kp is obtained from so first you have this is just proportional, right? So let me see. Let me see if you have theta double dot equal to minus A theta plus B times E theta. So E theta and this one is some compensation, I guess. Right, this one is some compensation, but it's not shown in the architecture. Where this is compensation. Actually, you don't have this in here. You don't have this in here, and yeah, sorry, you don't have in here. Uh, so you don't have this one in here. This one in here. Okay, so it's better for me to write down again. Um, new. Okay, let's start with the new one. So first you have the equation of motion v times va, and then you design a controller va equal to a proportional constant times error theta d theta e theta where e theta is equal to theta d minus theta actual theta. Okay, error theta. So from equation 1 here, you can rewrite it theta double dot equal to minus a theta dot plus b kp theta d minus theta. Then all theta you move to the left hand side. You have theta double dot plus a theta dot plus bkp theta, and then equal to bkp theta d. Yeah. Okay. So then you can analyze from this equation. It's a linear ordinary differential equation. Let's say if theta d is constant, if theta d is constant, then theta should be theta homogeneous plus theta particular, which is theta particular, which is equal to theta d itself, right? Because from what we have seen so far in the previous lecture, the homogeneous solution will die out after a certain period of time, which means theta h go to 0 when t go to infinity, right? Or you can say you might, yeah, you can analyze in this way. Theta steady state will approach to constant, and how you can find this constant? You can find it by first you find Theta steady state dot, of course, is 0, and then theta steady state double dot is also 0. So from the equation 2 you have 0 plus 0 and plus bkp theta equal to bkp theta d. So it means theta just equal to theta d. This is what we want, right? So it means this kind of controller, in some sense, is applicable in some case. The problem, the problem is that if you have uncertainty or disturbance, if you have disturbance in, yeah, somewhere, let's say from equation 2, well, I can say if we have disturbance, if we have disturbance, let's call it, um, let's call it D. Then one can be written as plus D, like this, and 2 can be written as minus D. So the question is that, can we still achieve theta approach to theta D when t approach to infinity? The answer is no, we cannot achieve this. That's why proportional controller in some case is not applicable. One more thing that proportional controller is not very good is that the transient. You cannot have a desired transient. Let's say, even though you don't have disturbance for the transient, yeah, let's say theta d is here. Uh, you design, yeah, let's say you want a fast response like this. This is can order. Let's say you want a fast response, but there's no overshoot. And if you design using proportional controller, you can have fast response, but at the same time you have oscillations like this. That is the limitation of proportional controller, right? Uh, I don't illustrate it now because you need to learn some more basics on Laplace transform and rule locus. So I will explain later again using rule locus. But just now, you just be aware that proportional controller has limitation. First, it's not robust to disturbance. Second, the faster response you want, the more oscillate it will be. Okay. Okay. The next control architecture. Um, Let me just snapshot this one to the next slide. don't keep it. So with me. Okay. So the next controller is proportional derivative. This one is proportional and this one is derivative. This means that the way you compute the supplying voltage is uh, the sum of constant times error and constant times derivative of the error. Okay. So again, you start from your model. You have theta double dot equal to minus a theta dot plus BVA. And then you choose, so here is your design controller. VA equal to KDE theta dot plus KPE theta. Okay. Um, or you can rewrite it KD times theta D dot minus theta D plus Kp times theta D minus theta D. Theta D, what I'm writing here. Theta D dot minus theta dot and here theta D minus theta. Okay. Um, then equation 1 here, I say 1 again. Uh, yeah, this one is equation 1. So equation 1 can be written as theta double dot equal to minus a theta dot plus b times kd here theta d minus theta here theta d dot minus theta dot plus b times kp theta d minus theta. Then you move all theta to the left hand side. Uh, so here we have a plus bkd times theta dot plus theta here bkp theta equal to bkd theta dot theta d dot plus bkp theta d. Then we can make analysis. If let's change color. If theta d is constant, then theta d dot is 0, right? And the solution theta of t is theta homogeneous of t plus theta particular of t, where you have theta particular just approach to theta d. Why? You can see here. You can see here if theta d dot is 0 and the, because theta d is constant here, the particular solution of theta is also constant. So this constant equal to this constant, which means theta approach to theta d, right? Because theta is constant, this one is 0, this one is 0. So theta equal to theta d. Okay, and this is what we want. We want theta approach to theta d. I mean this theta approach to this theta d, because the homogeneous solution will die out after a period of time. Okay, certain period of time, it will die out, provided that your system is stable. Of course, it means you choose proper KD and proper KP, and the system is stable. Then you can have theta approach to theta D after a certain period of time. And question again, whether this controller is robust to disturbance or not. Again, let's say if we have disturbance here. Oh, this is on the right hand side. Okay, so we have disturbance here, and if theta, even if theta d is constant, so theta steady state or theta particular solution is constant, but it cannot approach to theta d because of the disturbance terms, right? So again, uh, PD controller, proportional derivative controller, is not robust to disturbance. Okay. For the transient, yeah, actually the transient, now you have two parameters to play around. It means you can, to some extent, have a desired transient. Yeah, if you choose KD and KP properly. Okay. And I won't explain in detail for now. Uh, I will explain later. So, do you have any question up to this point? Li Huo, you have any question? You, any question? I don't have any particular question, but I'm struggling on the understanding of the diagram. Diagram? I guess with practice it will come. Not familiar with diagram? Or what do you want to say with the diagram? It's the diagram. Yes, so yeah, are you familiar with this diagram already? Or not really? Yeah, well, this block diagram, if you think about analytical way, analytical method, that's not the right thing to make, not the right thing to illustrate. Only numerical integrator is applicable with this kind of diagram. Okay, you understand? Um, if you, yeah, actually, if you want to uh, represent the modeling in an analytical way, you can choose, you can reformulate this part as like this. First, let h1 equal to theta and h2 equal to theta dot. Then you can have h1 dot equal to h2, and then h2 dot equal to minus a h1 plus b bva. Okay, and then yeah, and then if you can have analytical method to solve it, but for sure you can have because this is linear system, linear model. Um, then you can, yeah, you can simplify the blocks just like the system means this equation h1 dot equal to blah blah blah, h2 dot equal to blah blah blah. So you have, let's say you have a way to solve it. Then this one is just h. It means h1 h2. Okay. But h1 is theta, right? H1 is theta. Ahead you want to extract only h1, and this one you don't need. So you need h1 for the feedback, and this input is va. Yeah, something like this. And this is controller. Yeah, like this. So the whole system here is illustrated by this block. And you can say, oh, okay, inside this block I have a way to solve it for it, whether analytical or numerical method. And for here I use this instead of 1 over s, because when I make this lecture, I assume that the student do not understand Laplace transform, do not know 1 over s. So just write here integrator, numerical integrator over time. Okay. Any more question? No? Yes? Okay. Andrian? No? Right. Last controller, the proportional derivative PID, proportional integral derivative. Okay. So I missed the term integral. This is very, very popular, um, not only for controlling DC motor, but application in aerospace, application in chemical process, many other control system. PID is still the most popular one. Um, okay, we use the blue one. So I'm going to derive as the equation with the input as theta d and the output as theta, just like what I did earlier. So again, we can start from theta double dot equal to minus a theta dot plus bva, yeah, equation 1. And then we choose, okay, or we can say we design controller, which means the way you calculate the supplying voltage is like this: kd times e theta dot, yeah, kd times e theta dot plus kp times e theta plus ki integral 0 to t e theta dt, and then substitute this va into equation 1. So 1 can be rewritten as theta double dot equal to minus a theta dot plus b times kd. This one is theta d dot minus theta dot plus kp theta d minus theta plus ki integral 0 to t theta d minus theta dt. Okay. And then you take time derivative at both sides to drop the integral term. Okay. So here you can have theta triple dot plus, so here become theta double dot, here become theta double dot, theta dot here become theta double dot as well. So we can have a plus b times kd theta double dot, and then plus b times kp theta dot plus b times ki theta equal to bkd bkd theta d dot plus bkp bkp times theta d. Am I right? I think this one theta double dot, eh? Yeah, kd theta d double dot, kp theta d dot, and then plus bki bki theta d. Yeah. I should mention that then take time derivative on both sides. Right? So you can have this. And next, we can make analysis. Again, if theta d is constant, then theta d dot equal to theta d double dot, which is 0, and what? Theta of t approach to theta d when t approach to infinity, right? Now again, we pose a question. What if the system has disturbance? Will the controller be robust to disturbance? What do you think? Let's say we have disturbance here, and the disturbance still appear here. But then, when we take the time derivative both sides here, If the disturbance is constant, then it disappear here, right? So when we take time derivative, here it's just to drop the integrator part, but we can think in a opposite way. If we have this equation, uh, the disturbance is already this, let's say dot like this, and we integrate. Okay, we integrate to get the above equation. Then we realize that actually the integration term can deal with the disturbance. Okay, it means yeah, integral from 0 to t times some constant this uh, can cancel out disturbance, can compensate disturbance if disturbance is constant. Okay, so this is very interesting and very good. You need to know this. So whenever you want to design a position control system, you must think about what PD can do, what PID can do for. I mean, in order to get a good performance, given that your system have uptime or disturbance, what controller you should choose, something like that. And in even in DC motor, we have disturbance as a Coulomb friction, right? Coulomb friction, even it's small, it is disturbance. So if you choose PD controller, which is not robust to disturbance, then you cannot have a good performance. It means the error is not approached to zero. But if you use PID controller, then you have better, much better uh, performance. And if your motor is brake, let's say you impose a constant brake, and if you just use PD controller, the brake will make the performance poor. I mean, it cannot move. The rotor cannot rotate to the desired theta d. It just approach and then it stop. I mean, approach not asymptotically approach, but it has some certain error, which is far from zero. And then how can we choose theta Kp, Ki, and Kd properly? Now it's come to the most important moment, and then you need, because yeah, let's say just K, we just say Kp, Ki, Kd, but what are they exactly? How can we find them to have a good performance, right? Okay, because now I only consider regulation control. So I said many times if theta d is constant. What do I mean by this? We call this kind of control regulation control. Okay, this is a new term for you. Regulation control. It means we only want to regulate the motion to a certain constant, but we may change the constant from time to time. But when we let's say first I wanted the 90 degree, and then we wait for the motor to rotate to 90 degree, stay there for a certain period, and then you may want to move it to other degree like 180 degree, for example. Then the motor move there and stay there for a certain time, certain period of time. So this is called regulation. Another term is tracking. Tracking means you may want the motor, the rotor uh, to move to following a certain function. For example, a sine wave. I mean, in this period of time, the theta should move up to this angle. At this period of time, theta move to another angle. Continuously changing. For example, like sine wave, and that kind of control is called tracking. And the architecture of control that I showed earlier is only for, I mean, the performance is good only for regulation control, but not for tracking. We will see about tracking control later. Okay, but now the best moment to find, to choose the right KI, KP, and KP, KI, and KD. So I say here, I pose a question here: how can we find the proper KP first, KP, KI, and KD? Many people like to use trial and error, but it's not convenient. Actually, it's time consuming. Trial and error means you have apparatus, or maybe you start from simulation first. First, you randomly choose KPKIKD and run and check the simulation is good or bad. If it's bad, and then you try to change KP higher and higher. And then if you see that the performance even worse, then you drop it down, and then start to change KI. So, but it's very time consuming. Yeah, it's called trial and error. Another way is to analyze on the differential equation that we have done many times. So here, if I try to find the characteristic equations from here, can you remember this well? I need to copy it. Yeah, let's say, yeah, I'm only interested in the characteristic equation because I have already analyzed what happened in this state using the full equation. Um, okay, now let's see characteristic equation. So here you may say here is just zero, whatever. You just care the homogeneous solution, right? Just care homogeneous solution. Homogeneous. So the characteristic equation would be lambda square plus a plus bkd lambda, sorry, not square but 2 3, okay, and plus lambda. Okay, that term is bkp lambda and then plus bki equal to 0. Okay. So far you have analyzed before that if you have second order characteristic equation, then you have standardized form. But now you have third order. So what you can do with third order? Well, for the for the homogeneous solution, if you still have it in mind that if lambda is negative and it has large value, then the homogeneous term die out very fast. Okay? So from this property, you choose lambda 1 is, for example, minus 40, because if negative and the magnitude is high, then the uh, exponential term will die out very fast. Okay. So once you know lambda 1, I can uh, yeah, I can say choose the real roots. The first real root, I can say the first real root. Just call it minus lambda 1 equal to minus 40. Yeah, this way is better, more convenient. Okay. Then equation, the equation star can be rewritten as lambda plus lambda 1, and then you only have second order, right? Second order, and you can call it lambda square plus, uh, you use standard form, 2 times zeta omega n lambda plus omega n square equal to 0, and then expand it. Okay, expand it, lambda to the 3 plus lambda, this is lambda square, so it should be 2 zeta omega n plus the lambda 1 lambda square here, lambda 1, and then lambda square plus lambda times omega n here, lambda 1 times lambda here, so I can have omega n square plus 2 zeta omega n lambda 1 lambda, and then plus lambda 1 omega n. Please have checked, because most of the time I make mistake when explaining something. Yeah, I hope there's no mistake here. Then you make comparison with equation star. Okay, compare to the equation star. Okay. Make comparison between okay, then you can have what? I think Ki can be found easily. Ki equal to lambda 1 omega n square over b, and then Kp is omega n square plus 2 times zeta omega n lambda 1 over b, and then Kd equal to this term minus a over b. 2 zeta omega n plus lambda 1 minus a over b. Yes. So this is how you calculate controller, okay? Controller constant. And what is omega n and zeta? Omega n and zeta is how transient you want, right? How it looks. If you want the critically damped, which means zeta is equal to 1. You say, okay, I can allow it to have overshoot, a little overshoot. Then you can choose zeta less than 1. And omega n, yeah, you can choose, uh, for example, critically damped. Critically damped, zeta equal to 1, and omega n can be any. Okay, let's say 2 pi. Let's say if it is oscillate around, yeah, if it oscillate around the desired, you choose, let's say in 1 second it can oscillate uh, 4 times. So here it should be 2 pi times 4, like this. Okay, for omega n. Any question? Yeah. Sorry. Omega n. Lambda 1. Okay. Because for the homogeneous solution, theta theta homogeneous, you can have C1 exponential to lambda 1t plus C2 exponential to lambda 2t plus C3 e to lambda 3t. So I choose lambda 1 is minus 4t because I want this term to die out in a very short period of time, because exponential of minus 4t times t will go to 0 very fast. Yeah, you may choose minus 20, that's fine. Minus 30, that's fine. At least, yeah, but don't choose minus 2, minus 3 because it die out so slow. Okay. Yeah, you can calculate. Let's say t equal to 0.1 second. Uh, if t equal to 0.1 second, then e to the minus 40 times 0.1, then 4 minus 4, right? So equal to 1 over e to the 4. So approximately 1 over, this is, let's say e just only equal to 2 to the, so 1 over 16, right? Less than 1 over 16. So around just 0.0, I cannot compute it without calculator. uh, Maybe 0.3 something, right? Okay, so it's like in around, yeah, no, I don't consider C1 yet, but just want to check uh, how fast the exponential term e to the minus e to the lambda 1t die out. Okay, how fast it die out. Just want to check that. So I would say, yeah, it must the first root. Okay, the first root must be, if I write this way, here should be should be like this. Yes. Yeah. Should be like this. Lambda 1, lambda 2, it just conversion. Okay, don't worry about this part, just conversion. I want to write it because I want, finally here I want to have all plus sign. Do not want to have minus sign up here, and then can make us confused. Okay, okay. The most important point is that exponential to the minus, to the negative value, and make that negative value as big as possible. Okay, that's the point. But it's just my experience. Uh, Lambda 1 is 40 is already enough. Okay, I have tried 20. Yeah, it's slightly different. 40 is better. I tried 70, but no much change like that. Yeah, and using this method, you can save a lot of time comparing the method of trial and error, and you don't experience unstable case because trial and error. Sometimes you choose very bad KP, KI, KD, and then it become unstable. Then if you are working on the real hardware, and then it's maybe you can damage the hardware, something like that. Okay, any more question? If no, I end now.